So in the previous lecture, let us recall what we have did. So in the previous lecture, we have defined a complex numbers. So as you have know that we have defined a complex number as order set, which is also denoted by C or R square, which is the set of all order pairs xy such that x and y belongs to R, with certain rules and regulations. Or the rules, first rules is that we have defined as, so for that I need to take for any xy, x1 y1 and x2 y2 belongs to R square. If x1 y1 is same as equality rule is there, so if it is these two order pairs are equal if and only their components are equal, that is x1 is equal to x2 and y1 is equal to y2. The second rule that we have is the addition, how we define the addition. So if we can have x1 y1 plus x2 y2, so addition is defined as x1 plus x2 comma y1 plus y. The third is the multiplication x1 y1 dot x2 y2. So how the multiplication is defined as x1 x2 minus y1 y2 x1 y2 plus x2 y1. And the fourth rule is that in that we are saying that a complex number z is equal to xy is non-zero if at least one of the number x and y is non-zero. So this is the things we have discussed in the previous lecture. Also we have denoted this number, this order pair xy, and we conclude that we can write down that is in the form of x plus iy if we consider the order pair xy as x for any x belongs to R. And if you can consider the order pair 0, 1 and if you denote it by I, then we can write down this thing. So this sort of things we have discussed in the previous lecture. So in this lecture I am going to discuss about the further properties of complex numbers. That means what are the other properties of complex numbers have. So with the start with that, we are defining or discussing about additive identity and multiplicative identity. The additive identity is 0 equal to 0 0 and the multiplicative identity is 1, which is 1 comma 0 for real numbers carry over to entire complex or complex plane. They are the real numbers because as per this definition of as per this rule x comma 0 is equal to x, these two number x 0 which is order pair 0 0 and the 1 order pair 1 0 are the real numbers. So this two real numbers forms an additive identity and multiplicative identity respectively. Why we can see in this way? Because as you have this equation, that is 0 z plus 0 is equal to z, and you know z into 1 equal to z for any z belongs to, that we can observe and we can see. To see this, let u comma v be the additive identity. Then what we have is for any xy plus ub, we should have the same number x. So that will gives you x plus u, y plus v order pair equal to x. By equality rule, we can say that it is x plus u is equal to x and y plus v equal to. So therefore, what we can have is u equal to, because x and u are the real numbers, so x has additive inverse in real numbers, so that will gives you u equal to 0 and v equal to 0. So therefore what we can say is 0 0 is additive identity for complex number. Similarly, one can prove that. So I am giving you as an exercise this thing. Prove that 1 0 the multiplicative identity for complex. So the next thing that I am giving you is another proof. One can also prove that this 0 and 1, which is the order pair 0, 0, this is 1, 0, are the only complex numbers with such property. Now we are discussing about the additive inverse. So each complex number z is equal to xy and additive inverse minus z is equal to minus x minus y satisfies the equation z plus minus z equal to see this, let us take u comma b be an additive inverse of xy. So therefore what we have is u comma v plus x comma y equal to 0. This will gives you u plus x v plus y equal to 0. So therefore u plus x is 0 and v plus y is 0. So this will gives you u equal to minus x, because u and v are the real numbers, and in the real number the additive inverse of x will be minus x. So I am adding minus x both sides, so that's why we will have u equal to minus x and v equal to minus y, same. So therefore what we have is the additive inverse of, therefore minus x minus y is an additive inverse of order pair x. So I can give you one exercise here that is prove that there is only one additive inverse for any given z equal to. So for any given x y, there will be only one, that is the additive inverse is unique. Next is the multiplicative inverse. For any non-zero complex number z equal to xy, there is a number z inverse such that z into z inverse is equal to. So to see this, let us take uv be an inverse of z equal to. Inverse means here I mean to say that it is multiplicative inverse. So that is, hence what we have is, so therefore we have x into y into uv equal to 1, which is 1, 0. So therefore what we have is, as per the product rule, if I apply xu minus vyv comma xv plus yu equal to 1, 0. So that will gives you two simultaneous equation by comparing the real part or real component and then imaginary component, as xu minus vy is 1 and xv plus yu equal to 0. Now we need to solve these two simultaneous equations. So solving linear simultaneous equation for u and v. So we are solving this two equations. I am calling this as equation 1 and this will be 2. For that I am multiplying. So I am multiplying equation 1 by y and subtracting that equation from 2 by multiplying. If we do this operation, the equation 1 by multiplying y, we have xy u minus y square v equal to 1, and the equation 2, if I multiply by x, this equation by multiply by x, and I am writing this quantity first, so that will be xy u plus x square v equal to 0, and I am subtracting these two equations. This will have y here we have. If I subtract these two equations, we will have x square plus y square, v by commoning out v from it, y minus 0 will become y, so that 4v will have is minus y upon square plus y square. If I put this value, putting this value of v in 1, we get u equal to x upon square plus y. Please check this whether you get this u equal to this quantity. Hence what we have is, therefore the multiplicative inverse of z equal to xy is z inverse will be x upon square plus y square minus y upon square plus y. So one should note here the inverse of 0 is not defined. Because when 0 is there, that means if z is 0, means that x is 0 and y is 0. So that means that this denominator x square plus y square is not existing. So that's why the inverse of 0 is not defined. So further we will discuss about the commutative laws. So the commutative laws for addition and multiplication will be z1 plus z2 equal to z2 plus z1 and z1 z2 equal to z2 into z1. So I will say this is the property of complex number. So for the proof, you may see that consider z1 equal to x1 y1 and z2 equal to x2 y2. Then if I start with z1 plus z2, by definition of addition will give you x1 plus x2, y1 plus y2. Since x1 and x2 are the real numbers and real number with addition is a commutative under the real number, so that's why this will be, you can write as x2 plus x1, y2 plus y2. So this will gives you x2 by definition of addition, x2 plus x2 y2 comma x1 y2. So therefore this will gives you z2 plus z2. So therefore what we have is z1 plus z2 equal to z2 plus z1 for every z1 z2 belongs to. I am giving you as an homework this thing that we can prove this. So now according to this laws, Iy we may write as yi. Hence we can write either z is equal to x plus iy or z is equal to x plus yi. So both this quantity we may write. The next property we can say that it is associative property or associative laws. So that property that we have is for any complex numbers z1, z2 and z3, prove that z1 plus z2 plus z3 equal to z1 plus z2 plus z3, and second one is z1, z2, z3 equal to z1, z2. So the proof I am giving you as a homework. Okay. The next one that we are discussing about some basic property, or I can say subtraction. So the several other operations on complex numbers are to be defined. So the operation of subtraction is the inverse of addition, that probably you already know. So now if the difference z1 minus z2 it's called z3, then what we have is z1 minus z2 is equal to z2. Then z3 is the complex number that must be added to z2 to produce z1. So that means what we have is z2 plus z3 will be z2. Now as you know that z2 is a complex number, so it has an additive inverse. So I am adding additive inverse of z2 both sides. We obtain minus of z2 plus z2 plus z3 equal to minus of z2 plus z1. Now applying the rules of associativity here, we can write this as minus of z2 plus z2 plus z3, and applying the rules of commutative here, we may write this as z1 plus minus z2. So and applying the rules of additive identity, we may have this as 0 plus z3, and this we may write as z1 minus z2. And 0 is additive identity, so that's why we can write as z3 equal to z1 minus. So this way we can get z3. The next one is the division. So division is the inverse of multiplication, as subtraction is the inverse of addition. That is z1 upon z2 equal to z. If z2 into z3 equal to z1, provided z2 is non-zero. By keeping this mind, that is z2 into z3 equal to z1, we multiply both side by inverse of, we get Z2 inverse into Z2 Z3 equal to Z2 inverse into Z. By applying the associative property here, what we get is Z2 inverse into Z2 Z3 equal to Z. The Z2 is the Z2 inverse is the inverse of Z2, so that's why this will become 1 into Z3 equal to Z2 inverse. Now 1 is the additive multiplicative identity, so that's why this is Z3 equal to Z2. So hence we have the division, which is nothing but the Z2 inverse into Z1, which is Z1 upon. For that, if you have Z1 will be x1 y1, Z2 will be x2 y2, and Z3 if I consider x3 y3, then what we can have is Z1 Z2 inverse will be Z3. So Z3 will be x1 y1, and as we know that inverse we already established before, that says that it is Z2 inverse is x2 upon x2 square plus y2 square minus y2 upon x2 square plus y2. Now if you multiply these two quantities, Z3 will become x1 x2 plus y1 y2 upon x2 square plus y2 square and x2 y1 minus x1 y2 upon x2 square plus y2. Check this. That is, if you multiply this two complex number, either you will get this. So another way is to get this complex number is if you have Z3 will be Z1 upon Z2. So if you can write down this is as x plus iy1, x1 plus iy1 upon x2 plus iy2. If you multiply both sides by x2 minus iy2 upon x2 minus iy2. So if you can simplify this to quantity, or you can multiply this to quantity, that will gives you x2 square plus y2 square in the denominator, because it is x2 square. You can see that this will multiply to this one, iy2 will multiply by minus iy square, and I square will become minus 1. So this minus and that minus will become plus 1. So that is x square plus y, x2 square plus y2 square will have. Here in the numerator what we have is x1 x2 plus y1 y2 plus I x2 y1 minus x1 y2. So this is the quantity. This is another way we can simplify. For example, let us take the example. For example, if you have a number, so simplify 3 plus I upon 2 minus I. So if you can have this number, you just multiply and divide it by 2 plus I. So what will be this gives you? If you multiply this 2, this will be 4 plus 1. So in the, if you multiply this quantity by this quantity, it will gives me 4 plus 1, and this will gives you, that is 6 minus 1, because 3 to the 6 and I plus I is minus 1 plus I 3 plus 2. So that will gives you 5 by 5 I, 5 by 5. So that will gives me 1 plus I. So that is the things we have. This way we can calculate. Further property that we have is for any complex number Z1, Z2 and Z3, prove that the first quantity, that is Z1 into Z2 plus Z3 equal to Z1 Z2 plus Z1 Z2. This is called the distributive law. The second one is Z1 plus Z2 upon Z3 will be Z1 upon Z3 plus Z2 upon Z3. The next one that we can have is Z1 Z2 upon Z3 Z4. We can write as Z1 upon Z3 into Z2 upon Z4. So the proof I am giving you as an exercise, that you can prove that these three properties. The further property that I am writing or for discussing is, let Z1 and Z2 are complex numbers. If Z1 into Z2 is 0, then prove that Z1 is 0 or Z2 or both are 0. Both are 0 means Z1 and Z2 both of them are 0. So for the proof, so I am giving you two proof of this. So consider Z1 into Z2 is 0. So if Z1 into Z2 is 0, by definition, if you have take the Z1 equal to x1 y1 and Z2 is equal to x2 y2 or x2 plus I y2, whatever the notation you want to write down. So by definition of multiplication, we can write down this is x1 x2 minus y1 y2 comma x1 y2 plus x2 y1 equal to 0 0. By definition of equality in complex numbers, the components, if you compare, will have x1 x2 minus y1 y2 is 0 and x1 y2 plus x2 y1 is. Now what we have here is we need to prove that Z1 is 0 or Z2 is 0. So without loss of generality, I may assume that if Z1 is non-zero, then we need to prove that Z2 is 0. So if the Z1 is non-zero, that means x1 is non-zero or y1 is non-zero. So any one of the quantity x1 or y1 is non-zero. So without loss of generality, I also assume that x1 is non-zero. If x1 is non-zero, this equation 3 if I denoted, and if I write down this is as equation 4, then from equation 3 what we can write is x2 equal to y1 y2 upon x1 due to x1 is non-zero. So by putting this value of x2 in 4, we get, so if I put this value in this equation, what we get, x1 y2 plus y1 y2 upon x1 into y1 equal to 0. So if you can see, observe this, and if you can take this x1 as an LCM, so what we have is x1 square y2 plus y1 square y2 equal to 0. So if you further simplify, x1 square plus y1 square into y2 is 0. So that means y2 will be 0 because x1 square plus x2 square is non-zero as per our assumption. So y2 is 0. So if y2 is 0 or x2 is 0 because of equation 3. So we have x1, x2 and x3. So we have x2 is 0 and y2 is 0. So therefore, if z1 is non-zero, then z2 is 0. So that proves our theorem. So I am giving you here another proof for the same statement. So now, if z1, z2 is 0, if you assume z1 is non-zero, then z1 inverse is exist. So if it is exist, you can multiply f inverse to this equation. So I will start with now z2 equal to z2 into 1. But z2 into 1 will be z1 into z1 inverse. So this by associative law, before I am applying the commutative property, we will write this as z1 into z1 inverse into z2. Again by using the commutative law, we can write down this is z1 inverse into z1 into z2. By applying the associative property, we can write this is as z1 inverse into z1 z2. And this z1 z2 we already have 0. So any number which multiply to 0 will tends out to be 0. So thus what we have is, if z1 z2 is 0, then either z1 is 0 or z2 is 0 or both numbers z1 and z2 are 0. So these are the properties that we have discussed. Let us recall what we have did in this lecture. So in this lecture we discussed the certain properties. The first one is the additive identity, that is 0 plus 0 is equal to 0 equal to 0 plus z for any z. Then multiplicative identity, that is z into 1 will be z, which is also same as 1 into z for every z. Third one, we have commutative law, For addition as well as for multiplication, that is Z1 plus Z2 is same as Z2 plus Z1, and Z1 Z2 is same as Z2 plus Z. That is for every Z1 Z2 complex number. The associative laws, that is Z1 plus Z2 plus Z3 is same as Z1 plus Z2 plus Z3. Z1 into Z2 Z3 will be Z1 Z2 into Z2 for any complex numbers Z1 Z2 and fifth rule is we have seen the distributive law, that is Z1 into Z2 plus Z3 will be Z1 Z2 plus Z1 Z3 for every Z1 Z2 Z3. The sixth rule that we have discussed is Z1 plus Z2 upon Z3 will be Z1 upon Z3 plus Z2 upon Z3. The seventh rule that we have discussed is Z1 Z2 upon Z3 Z4 will be Z1 upon Z3 into Z2 upon 8 that we have discussed, that is Z1 Z2 is 0, which implies Z1 is 0 or Z2 is 0 or both numbers. So that's it for this today's lecture. Thank you very much. Please do subscribe and like the Shanti-Peace for mathematics. Thank you.